All right, welcome back. All right, so let's look at our third Thevenin problem that we have. Right, so this one is asking us to find V Thevenin and R Thevenin. Okay. So there we go. So V Thevenin and R Thevenin. So let's go ahead and look at this, what we have. So we only have one battery source, that's fine. All of our resistors, that's good. But notice here now we have A and B. These, you'll see this sometimes with Thevenin problems. This is still just plus and minus down here, okay? This is VOC. But you'll notice this weird thing called a load resistor, okay? So this R of L. So now, instead of us adding just a regular wire, what we'll do is add that resistor on there. And this comes into play towards the very end of the problem. But let's work it like a regular problem, and we'll see how that plays in just a minute. Okay, so step one, dependent sources. I don't see any. We are good. So let's zero out our sources. Zero out sources. We'll turn our batteries into wires, and we'll turn our current sources into clipped out wires. Okay. So if we go over here and we redraw our circuit, '47. This is 22. And this will be 100. And this will be 100 as well. And we took our battery and we just replaced it with the wire. And now plus, minus, and then VOC. Remember, we're going to treat it like a battery. So now let's work that way. Find our R equivalent. So I'll see first off that these two are going to be in series. So I can write R series 1 will be 47 plus 22. Which will give us 69 ohms. So if we go and redraw that, there's 69 right there, 100 right there, and 100 right there. Still have our plus minus right there. Okay. And now I can see that these two are going to be in parallel. So I can go ahead and write R parallel 1. It's going to be 100 times 69 over 100 plus 69. Okay. It's going to give me 40.83 ohms. Okay. So if we go and combine that, so we go and combine that. Drop our VOC here, plus minus. This is the 100. This is the 40.83. Then we see these last two here are in series. So I can say R series 2 will be 100 plus 40.83. And that'll give me 140.83 ohms. And one last redraw. 140.83 plus minus VOC. So this is my last resistor. So my R equivalent is equal to my R Thevenin, which is 140.83 ohms. So that's part one. So we have found R Thevenin. Now to find V Thevenin or I Norton, we'll jump back to the original circuit. So our original circuit is going to have plus minus, this is 10 volts. $100 right here, 47 right there, and 22 right there. And we also have that last 100 here. We have open terminals A and B, where this is plus minus and this is VOC. So even though it's connected up here in the original problem, just know that it's going to be right there. Okay. So if I'm this battery source and I'm sending current out this way, sending current like that, I will travel up through here, go into this resistor, hit right here. I'll see that this branch is open, so I will not go down that branch and travel down these two resistors instead. And I'll complete my circuit there. So I'll have this I just circling around. And like we have done in previous problems, if I know that these are parallel, so if I can find the voltage from here to there, find that voltage drop, then I find voltage drop from here to there. So what can we do? We have one loop and with a bunch of resistors on it, where no current travels down this branch, no current travels down that branch. So effectively, that is my circuit. So let me do a voltage division. So if I go do a voltage division, and I want to find from here to there, let's make up a name for it. We'll call it like, I don't know, like VA. That's fine. So V of A will be the branch resistance, so resistance of the branch, over our total times V of S. And remember, this is in series. We can only do this if it's in series. Okay. So our branch is going to be at 47 plus 22, but the total is going to be 100 plus 47 plus 22. Okay? Because you can think of it as a percentage of how much a voltage is being sucked up. Times 10 volts. And this is going to be 69 over 169 times 10. And this is going to give us 4.08 volts for VA, which is equal to V Thevenin. So that is our VThev value. All right. But we're not quite done. So we now found V Thevenin. And I realize it only says V Thevenin and R Thevenin, but yeah, there's more to it. I just forgot to type it up. But it wants us to find current through the load. Okay, so current through the load. So what this will look like is if we go and draw our Thevenin circuit. So Vthev, Rthev. Remember, this is 4.08 volts, and this is 140.83 plus minus. But now, let's drop a wire and let's throw our load on there. Okay. Now we want to find I short circuit. Actually, let's call it I load because we called it I load earlier. So basically, what we want to do is just find the current through this load resistor now. Okay. And what this means is that I load is going to be just V Thev over R equivalent, because now it's just current that's being induced through the entire thing. So that whole current. So it requires all of the resistance. So Vthev is 4.08 volts. Our equivalent is 140.83 plus. We said our load is 1 kilo ohm. So that'll be 1,000 ohms. So when we do that, we're going to get 0.00357 amps, which is equal to 3.57 milliamps. So that's I of load. But don't click away quite yet. There's something else I want to show you. So in the concepts that I was talking about, well, what if we wanted to change the resistance? Why the heck are we even doing all this? So what if I was to say, okay, what about now I want my R load to equal 500 ohms. So now my whole analysis changes, because if I was to come up here and do this problem and do this whole problem again, I would have to go back, find the R equivalent, find the voltage division, do the current. Like, it's a lot of work. Whereas right here, I can just go, okay, I've load now is going to be Vthev over R equivalent, which is just at 4.08 over 140.83 plus, now instead of 1,000, it's just going to be 500. And that'll give us 0.00637 amps, which is 6.37 milliamps. Okay, so now we did all that. We found this whole Thevenin circuit just so we could prevent ourselves from having to do all of the analysis over again. So we can now freely, essentially, go change this resistor out, this load resistor, that one right there. We can take it out and change it as much as we want, and we can now determine the current through it by doing just one simple calculation. So it's a very neat trick, and this actually plays into charging and discharging with capacitors and inductors. So it's a very, very useful tool. But yeah. Hope this cleared some stuff up for you. I'll see you in the next video.